A very good day to all. With immense pleasure, I welcome you all to the first webinar of Raman Optronic Webinar Series, ROSE 2023, organized by Raman International Optronic Society, LEOS, in association with the Department of Optoelectronics, University of Kerala, and LEOS University of Inaugural, Slovenia. Today, November 7th, is the 12th anniversary of the Nobel laureate SRIRAM, one of the greatest Indian physicists of the modern era. He is remembered for his marvelous scientific accomplishments. Today, we are very proud to have a distinguished scientist, Dr. K.V. SRIRAM, Director, Laboratory for Electro-Optic Systems, ISRO, who has played a crucial role in the Chandrayaan-3 mission, as our speaker to share the success story of Chandrayaan-3. I welcome the Chairman of LEOS, Professor Raman, for the welcome address.
Thank you, Dr. Sapna. Good evening. Most respected Professor Dr. K.V. SRIRAM, Director, LEOS, ISRO, Bangalore, India. Respected professors, members of Raman International Optronic Society, LEOS, friends, organizing committee members, students, and esteemed participants of the webinar. Gaining impetus from the overwhelming support and participation received from the global optoelectronics fraternity to Raman Optronics Webinar Series ROSE since 2020, LEOS is organizing the 4th Virtual International Conference ROSE 2023 from 7th November to 30th November 2023 in association with the Department of Optoelectronics, University of Kerala, LEOS, University of Nova Gorica, Slovenia. All the webinars in ROSE 2023 are scheduled at 7 p.m. IST on all working days except on November 11th with the same Google Meet link. Today is a significant day for the optoelectronics and physics community as we celebrate the birthday of the renowned scientist Sir C.V. Raman. To honor his legacy, the inaugural lecture of ROSE 2023 is dedicated to the Raman Memorial. We are fortunate to have Dr. K.V. SRIRAM as the speaker for this special event. LEOS was formed with the vision of global interaction and sharing of knowledge in photonics, optoelectronics, and optical communication, and with a mission to provide a platform to bridge the gap between academia and industry through collaborative research, webinars, and research paper presentation. The success often results from the combined effort of a dedicated team and hard work. The credit for the success of previous ROSE webinars can indeed be attributed to the LEOS organizing committee members. The conference aims to provide a platform for the young minds to bridge the gap between academia and industry and to showcase their innovations through research paper presentations scheduled on 25th and 26th of November. I request your active participation by submitting research papers to the conference. ROSE webinars are blessed by the very participation of the giants in optoelectronics, not only as speakers, but also as participants. I would like to thank the speakers of previous ROSE webinars and organizing committee members of LEOS for introducing new faces to ROSE 2023. Considering the overwhelming participation and acceptance to the webinar, we are giving live streaming on YouTube and also on our YouTube channel, Raman Optronics. I request all of you to subscribe and view the previous ROSE webinars. Now there are more than 1,200 registrations to ROSE. If you have not registered yet, I request you to submit the registration from the link through the link given in the chat box to receive the updates of future webinars and LEOS membership certificate. There is no registration fee. Today, we are fortunate to have Dr. K.V. SRIRAM, Director of LEOS, ISRO, India, with us as the speaker who has made invaluable contributions to Chandrayaan-3 mission. The success of ISRO's Chandrayaan-3 mission has filled every Indian with pride, establishing India as the 4th country to successfully land on the moon and the first at the lunar South Pole. We are thankful to you, sir, for accepting our invitation to the webinar. On behalf of LEOS, I welcome Dr. K.V. SRIRAM to the webinar series. I also extend a warm welcome to the esteemed professors, researchers, students, and all those who have joined us for the first webinar of ROSE 2023. Requesting your wholehearted support and participation throughout the program to make this a grand, memorable event I invite one of the secretaries of LEOS, Dr. Swapna, Laboratory of Environmental and Life Sciences, University of Nova Gorica, Slovenia, to introduce the speaker and to chair the session. Over to Swapna.
Thank you, sir. As we all know, Chandrayaan-3 is the third mission in the Chandrayaan program, a series of lunar exploration missions developed by the Indian Space Research Organization. India has made history as its moon mission became the first to land in the lunar South Pole region. With this, India joins an elite club of countries to achieve a soft landing on the moon after the US and former Soviet Union and China. It is an absolute honor to introduce a distinguished scientist, Dr. K.V. SRIRAM, who has made invaluable contributions to the Chandrayaan-3 mission. Dr. K.V. SRIRAM obtained his PhD degree from Indian Institute of Technology, Madras in 1993, and then he joined the Indian Space Research Organization, ISRO. He took over as the Director of Laboratory for Electro-Optic Systems on April 2020. He is leading the LEOS fraternity to realize various types of high-accuracy altitude sensors, navigation instruments, and high-performance optics for remote sensing, meteorology, navigation, interplanetary, and science missions of ISRO. Previously, he spearheaded the optics developments at LEOS and was instrumental in the successful realization of TESS, ResourceSat-2, Cartosat-2 series payload optics, and AstroSat UV telescope mirrors. In recent years, he led the development of meter-class ultra-lightweight, high-performance Cartosat telescope, multi-band OceanSat-3 lens assemblies, Chandrayaan-3, and Aditya L1 special purpose optics. His expertise include development of large aperture high-resolution optical systems, multi-element lens assemblies, manufacturing and testing techniques, high-precision optical alignment, interferometric testing, and characterization of space optical systems. His other research interests include development of high-performance electro-optic sensors, laser and fiber optic instruments, MEMS, and detectors for space applications. He has about 80 publications to his credit in peer-reviewed journals and international conferences and delivered many invited talks. He is a recipient of the Harbans Singh Memorial Award from Optical Society of Sami Anveshak Award from the Society of Aerospace Manufacturing Engineers India, ISRO Team Awards, and the ISRO Individual Merit Award for the contribution to the Indian space program. He is a distinguished fellow of the Optical Society of India. On behalf of all the LEOS members, I welcome you, sir, to this webinar. And I also welcome all the invited guests and participants to the webinar. A humble request to all the participants, kindly ensure that your microphones remain muted throughout the presentation, and also take care not to present your screen in between. After the talk, time will be given for interaction with the speaker. Participation certificate will be provided only to those who submit the feedback in time with the link given in the chat box, which will be given at the end of the webinar. Now, I kindly request Dr. SRIRAM to start the presentation.
Thank you so much, Dr. Swapna. I think it was a wonderful introduction. And let me also immensely thank Professor Shankar Raman, who has been instrumental to bring me to this forum. I think it's a great honor for me to be, part of this particular LEOS as well as LEOS 2023. Okay, thanks once again, and let me warmly invite everybody for this talk. And the time is so apt. This particular Chandrayaan-3 success. I think the entire globe has been very jubilant on this and what it really means to India and to ISRO. So I thought it will be a very apt topic to talk on this Chandrayaan-3 today. So my topic is going to be unveiling this Chandrayaan-3 Triumph. What factors led to this mission success? So I'll focus on many of the aspects which has led to this success one by one. Given this big time, I think I will be able to cover the topics which I wanted. So India's lunar program started way back in the early 2000 itself. It was in a slow mode initially when we started somewhere in 2003, 2004, and the sanction happened from the government somewhere in 2005. From then on, I think we got into this subject into a lot of resolving this technical aspects what are required for this. And since Chandrayaan-1 is going to be the first of its kind interplanetary type of mission, so a lot of techniques need to be developed. And all said and done, I think we were geared up to go for this Chandrayaan-1 launch around October 2008. If I remember, the date is around 22nd of this October 2008. I think we were well prepared, and then we had configured the payload in such a way that it has an orbiter, an impactor, and many scientific payloads to carry out studies on the Chandrayaan. It's going to be only an orbiter. We didn't plan a landing at that time. So essentially, it has to operate at about 100 kilometers altitude from the moon's surface. The idea is, first we need to get into lunar orbit, and for that a lot of maneuvers, earthbound maneuvers are required, as shown in this particular figure. There were several earthbound maneuvers which were successfully done, and then lunar orbit injection also was successful, and in lunar orbit also we made several maneuvers before reaching this intended orbit of about 100 kilometers circular orbit. The payloads which were used were essentially to do a lot of mapping, essentially on chemicals and mineralogy, what could be present on the lunar surface, and also create a kind of a topography on the lunar surface. So essentially, we wanted to create a kind of lunar atlas and keep it ready to venture in further missions, how we are going to plan for landing and other things. So some of the important payloads which went into this are the terrain mapping camera. As you see here on this right side, one of the craters which have been imaged by this terrain mapping camera with a beautiful resolution. We also had some hyperspectral imager. Also, we had a laser lunar ranging instrument, and that was the first time we made use of a laser instrument for studying the, ranging the lunar surface. It also had an high energy X-ray spectrometer. And what I have shown in a different color, this is the moon impact probe, which really created some ripples in the scientific community, followed by which we had some foreign payloads also. One of that is that MCube, what we called Moon Mineralogy Mapper. So these two things created a real rage, I should say. In fact, when that impactor hit the moon somewhere near that Shackleton crater, we got some signals that there could be some presence of hydroxyl molecules, but we were not very sure to confirm it. But NASA was having a better instrument called this Moon Mineralogy Mapper, so which clearly said, analyzed and confirmed that there is going to be definitely these water molecules present in the form of water ice. So that really created a big this one to revisit, not only by India, by several other countries to take a revisit on lunar surface. So this is how our lunar program started off. Subsequently, we had plans to have some landing on the moon, but for that technologies will be of different dimension. So in the meanwhile, we also had a kind of commitment for several other missions, like Mars orbiter mission was committed by ISRO somewhere in 2013. We wanted to do that, and then followed by that this astronomy people demanded we wanted one astrosat. So we were committed for that, as well as for our routine remote sensing, as well as our communication satellites. So essentially, Chandrayaan-2 was slightly offset compared to Chandrayaan-1. We took more than a decade to develop this technology, and of course, we need to have technologies to land on the moon. So all took sufficient time to go more than a decade to follow up with this lander mission. And unlike Chandrayaan-1, we need to have powerful rockets. PSLV will not do, so we have to essentially go for GSLVs with cryogenic stage engines. So this particular spacecraft of Chandrayaan-2 was configured with an orbiter, a lander, and a rover. So idea is to have one orbiter there, then a lander will detach from that and then go towards landing of the moon. Once the landing becomes successful, then the rover can be deployed. So already we have experienced the kind of earthbound maneuvers. So that was also going through smoothly. We also had a wonderful lunar orbit injection, and then the transfer trajectory was very smooth. We were quite successful in putting that orbiter in the right orbit as planned. So we entered moon's orbit, and after some deboost phases, we got this lander separated, and then we at a conducive time we planned to land. But very unfortunately, that some 2 kilometers just above the lunar surface, we lost communication with the lander, and then later we understood that it has really led to a crash landing there. So the reason which was found out by that failure analysis committee clearly brought out several reasons, out of which one of the major reasons which is pointed out is about software glitch. There were many other technologies which were developed, but we could not demonstrate during that time. But then we were a little bit offset in terms of our efforts, what we have put, and then we wanted the Chandrayaan mission to continue in a very short time. After 2019, as you all know, that entire globe entered into a very bad phase of the pandemic, and also we were forced to offset our programs which we have kept for quite some time. But essentially this helped us to get into learning better technologies, what we could not do during the Chandrayaan-2 time frame. But Chandrayaan-2 today, even that orbiter is doing very fine. We had a beautiful mapping of moon with a 0.32 meter resolution at 100 kilometers. The entire lunar surface has been mapped. Now we also have something which is equivalent to that of lunar reconnaissance camera, which was done by NASA. And sometimes NASA even resorts to seeking some of this information what they want from our cameras, specifically this orbiter high resolution camera and the terrain mapping camera. So which we have flown in Chandrayaan-2, and which also aided in stereo imaging. And then that was the time frame where we also learned about how to do this digital elevation model generation. So really we could map all the craters and boulders. We could create an hazard map, and we were very much prepared even during the time frame given for Chandrayaan-2, how to identify a safe and soft landing for the lunar surface. So with this kind of technology developments, we ventured into Chandrayaan-3, that is the third lunar exploration mission. And this is the one, actually the Chandrayaan-2 also was towards South Pole. So we didn't change our objective. We wanted in the lunar South Pole only landing. And we have expanded all the whatever technologies were done earlier for Chandrayaan-2. Either we attempted to improve it or find something which could be done, as an innovative thing also. So some technologies were added as a new technology, and essentially we were very confident that this time we are going to be successful and we'll definitely land at the designated site. And also we had a lot of scientific instruments which were packed in the rover, and one such instrument, one or two instruments I'll talk about in my future slides. This is about how to carry out a spectroscopy study as well as lunar surface related studies. So what made the difference for Chandrayaan-2 to be a successful one? These are the special tests which have been carried out. Of course, some of these things could be done, but these are all short-circuited during Chandrayaan-2 time because of some time constraints. So one is this integrated cold test module where, very importantly, all the subsystems, including sensors, communications, everything was put in loop, except the engines were only shut off, and all things were along with the onboard computer. This was tested as an ICT module, and this test was conducted at Chitradurg in the Karnataka region, where we have flown this ICT module on a helicopter and then seen that all the sensors and other subsystems performed to the expectations what it was supposed to. Of course, there were certain learnings. We found some gaps where there were some false triggers. All those things could be corrected. And then we prepared ourselves for the subsequent tests. And we also conducted one more special test called integrated hot test. This was done at our launch pad, that Sriharikota, wherein a crane was deployed. And this is something like a realistic landing situation where, all the sensors in the loop, when we let down this particular scaled down model of IHT, it will exactly emulate that what it is going to have in that lander module. And then we have found out certain things which further need to be corrected in terms of our sensor performance. Those things were also carried out. And additionally, we also had a setback when we tested our Chandrayaan-2. That lander leg got damaged when we did the initial test. So just before the launch of Chandrayaan-2 also, there was an offset in time. So this time we ensured that the lander has been ruggedized very nicely. So, and then we could successfully carry out this drop test of that lander in our own eyesight at Bangalore. So a special test bed was created for this, and then we have tested even from about nearly 2 meters from there. If it is dropped, it won't experience any kind of damage on the legs or to any of the subsystems there. So essentially, this Chandrayaan-3 was launched using our, the famous what we call as our naughty boy, that Mark III of GSLV. Which initially created some kind of setbacks, but then we perfected all the technologies, and this is the fourth in that generation. The first one was used for Chandrayaan-2. After then we had 2 successful commercial launches, that M2, M3. Then M4 was used for this. This is our giant GSLV, which is about nearly 45-meter high and 4-meter wide, which has a capability to carry 4-ton mass to geo transfer orbit, and nearly we had equivalent mass for our Chandrayaan-3 in terms of all this propulsion module, and then we also had this lander, and inside the lander was the rover. So this time we didn't call it as orbiter. Instead, it is called a propulsion module. Since an orbiter is already existing, so what we thought is we will carry more propulsion, more fuel, so that in the event we encounter any kind of disturbance during transit orbits, still we will be able to manage. And some other ideas were there, which I'll little bit express in my future slides. So this launch also took place at SHAR, and then it was on 14th July in the afternoon, and then we could park our spacecraft in an elliptical orbit at 170 by 36,500 kilometers. Quite successful through its journey, 3-stage rocket. And the spacecraft is very similar to that of what we used in Chandrayaan-2. Instead of orbiter, as I told, this is a propulsion module over which a lander is put like a double-decker system. And inside that lander, we had this rover system. So the mission maneuvers, what were done is captured in this particular slide. So the rocket has perfectly parked at 170 kilometers, as I told, in that highly elliptical orbit with an inclination of 21.4 degrees. And from then on, we carried out, earthbound maneuvers. There were a total of 6, 4 in perigee position, 1 in apogee, and 1 for translunar injection. So this is how it is captured, how it has gone through different orbits, and then this lunar transit inject. And then followed by that, we got into lunar orbit. There also we did nearly 5 lunar bound maneuvers, which were quite successful. And then we carried out deboost maneuvers, which I'll explain a bit later. So we attained this 100 kilometer by 100 kilometer circular orbit. And then everything was to a perfection till this time. And then in the deboost, just before the deboost phase, we need to have this propulsion module to be separated from the lander module. And this operation also was quite successful. So propulsion module was revolving around the moon surface like the orbiter, and then lander module went through deorbiting stages. So there were 2 specific deorbits which were done to make it conducive to in one of the elliptical positions where it attains lower perigee, periloon we should call it. It's not perigee. So that came around about 25 kilometers towards the lunar surface, and we were looking at an appropriate time for landing. So this landing was aided by No, very importantly, sensors play a major role in the successful landing. Leave alone all these other subsystems. Anyway, they will perform all the propulsion systems, communication systems. Several other systems are there in the spacecraft, but it's important that sensors have to perform to a perfection to make it a safe and soft landing. So for this, our navigation and guidance control loop, which takes control from these sensors, is looped in such a way that inertial sensor is the main one which takes the input towards navigation, but this is aided by these absolute sensors. This is where LEOS plays a major role in creating these absolute sensors, because inherently inertial sensors will have a drift which will get corrected by the inputs of absolute sensor in the navigation filter. So we had some very specific specialty sensor like LERAP, laser gyro based inertial reference and accelerometer package. It's called LERAP. I'll explain each of the sensors a bit in my upcoming slides. And followed by that, we had this microstar sensor. Microstar sensor is the one which, for any spacecraft, for a lost in space condition, this is the one which clearly defines where the spacecraft is going to be. It takes image of stars and then creates a map, which can be compared with the stored catalog and then arrive at where the spacecraft is. A very important sensor for this mission. And altimeters, which is both based on lasers as well as RF based. And velocimeters is very important as we turn towards turn 90 degree and then descend towards lunar surface. Velocity judgment has to be very accurate. So for that we had some velocity sensors, and once we reach a very closer surface to the lunar surface, then we need to have some mapping which is based on some vision cameras. So this is called hazard avoidance kind of maneuvers which we have to do. And once we come very close to the surface and then touch, we need to have some sensors where it really senses the touchdown on the lunar surface. And each of these sensors, if you see in this particular chart, each one has a redundancy. That is what we have built in Chandrayaan-3. So for a laser altimeter, RF altimeter, K-band altimeter acted as a redundancy. And for a laser Doppler velocimeter, we have made this horizontal velocity camera, which is redundant to that. And also hazard avoidance camera, though it's a single camera, it can operate in 3D and 2D modes, which I'll explain a bit later. So all this redundancy was built, and even if one fails, the other one will take care. That's what we have ensured during this descent phase. So to capture in one particular slide, all this electro-optical sensors which we have made is this LERAP, which was done by IASU, microstar sensor, LASA, LHVC and LDV were done by LEOS, and then LHDAC by SAC. We also had that RF, it doesn't come in the category of electro-optical sensors, but then that also was one sensor which was very helpful. So let me get into this particular subject of how each of these sensors are configured and what is the functionality aspect of each of this. So the first one is this inertial navigation system, which right through the entire maneuver, this is one sensor which has to work from start to end. So this is based on a laser gyro. As you know, this works on a gyroscope type of principle, but it is aided by a laser system, and also it had an accelerometer package in that. So essentially, it measures that angular velocity and then relative velocity at certain feedback interval, which is about 8 milliseconds. And as you see in this picture, you have 3 of these sensors which have to function mainly, and one happens to be a hot redundant. So 4 of these, the sensor heads were kept in a skewed tetrahedral configuration. So one acts as a hot redundant here, and then electronics package is separately kept. So this also has one specific feature that on board, if there is a bias, that can be estimated and then compensated. So this is the beauty of this sensor. And then these are some of the specifications. I'm not going to go through each one of that, but how important it is, in terms of what values we have achieved is very important. We have what is specified here. Better than that, that value is what has been attained during ground tests. And this, as I told earlier, this navigation sensor is the one which performed right from launch phase till touchdown. And that accelerometer based cutoff is very important when we do this deboost space on the lunar surface. So the resolutions what we have got in terms of bias stability, or it is going to be velocity resolution, has been a factor better than what has been tested on ground is experienced on the lunar surface. So the next one is this microstar sensor, which is a very important sensor, as I told you. So this is a lost in space kind of absolute attitude sensor. So it is a version which we have developed as a third generation type of star sensor in our LEOS. So it's a lesser mass of about 1 kg, and then it uses an optical system which images the stars onto a CMOS detector, and we also have a processing electronics built around this behind this optics just before the detector, and then based on a FPGA based processing system. And also we also had this kind of a mini baffle. This is to prevent the stray light entering, because we are going to see only faint stars, faint light from stars. So essentially, unwanted light should not enter to create any kind of disturbance. So a beautiful system which has been configured in-house and then qualified. And this is the one which gave an update for through and through. When the satellite was put into Earth orbit itself, it started functioning, and all the time before any kind of burn is done, that earthbound maneuvers and all. No? So this is the one which will take an update and then correct the inertial system. And that update has gone at the right time before every type of maneuver which was carried out, and even before power descent phase, that is before getting into lunar landing. We have taken data of this particular one 74 seconds before that, because this is the one which will say exactly where we have landed, because post landing also will take one more input from this, just to validate where it has really landed and how much it is tilted with respect to other sensors input. So this is a very mission critical based sensor which has performed very nicely, and it has given gyro calibration within about 36 arc seconds accuracy. And also we got knowledge of just before start of the descent phase within 32 arc seconds. So this has a 3-axis type of sensing, wherein both side accuracies of the order of each axis is around 10 arc seconds, and then the last axis around 40 arc seconds. As a cross axis accuracy, it will all be within 10 arc seconds. So this shows in terms of this is computed as a quaternion. So it says how we have started just before the descent phase, and we went through this braking phase, which I'll explain a bit later. But it has performed exactly what we wanted. The third important one is called this laser altimeter, LASA. This is also an absolute category of sensor which is meant for ranging, and this measures line of sight type of landing. But this was kept in a canting angle with respect to the spacecraft, so it will be seeing a different surface from where it is going to land. So we need to do a necessary computation where exactly the spacecraft is going to be there with respect to body axis of the spacecraft. And this is this particular sensor works on the basis of time of flight principle. That means the round trip time what the laser pulse takes to go hit on the lunar surface and come back is a direct measure of the range or the altitude. And this is done with a laser which is an erbium glass 1534 nanometer laser. And if you look at the specifications here, it has to cater to a wide dynamic range, right from 17 kilometers down to about 5 meters. To cater to this high dynamic range, we need to keep 2 receivers apart from one transmitting laser. So 2 receivers were configured, as you see in this picture. You see this one big receiver, and then adjacent to that a small receiver, and then in between that is our laser transmitter. So this also was very useful when we came to this power descent phase. And this is exactly the height measurement what it has done during that whatever we call that 720 seconds of descent phase. And you see the perfection what we have got with this kind of sensor. The expected slant range as computed and to that of what is measured with LASA is almost a perfect match here for that line of sight. And this we expected only it can perform up to maximum 10 meters, but it has gone down up to 5 meters as well. The next sensor, which is very important, is this lander horizontal velocity camera. Its importance, I'll explain why at a later point of time. But this is a very important sensor in terms of, only sensor which is based on imaging. So this is again a navigation sensor, but how it computes is based on Fourier transform technology. What is being done here is, if you have two images of a lunar surface, shifted in space, that means in spatial domain, if they are separated, then in time domain, it's equivalent to multiplying by a phase factor. So essentially, a phase correlation is what is done in this sensor, and based on the image registration, what we had in our camera, and then we calculate this pixel shift and then take the data from altimeter, what I explained earlier, also the attitude from the star sensor, updated star sensor input to that navigation, and then obtain the velocity based on this. So essentially, it's not an absolute category, but it is. It essentially serves the purpose in terms of keeping it as a redundant for absolute velocity sensing. And being a vision camera, it doesn't demand any power, and mass is also very low, and it can operate in both imaging mode as well as velocity calculation mode. Because as we transited through Earth orbit, it has taken pictures of Earth. When it reached lunar surface, it has taken pictures. And then it was operating right from 31 kilometer down to about 20 meter. It was targeted, but then this also has performed to less than 10 meters. And very importantly, this sensor is mainly useful when we do this hovering on the lunar surface. So this was done at two intervals, 800 meters and 150 meters. And what input it has gave at 150 meters has become very crucial for safe landing, because it gave a correction at the nth moment. And when really about less than 20 seconds was available, it has given a correction on velocity to navigation to the tune of about 0.41 meters in the north and to 0.9 meters in east velocity, which really led touchdown to be to be a very soft landing. As otherwise, this correction would have, if this correction was not done, it would have accumulated an error of nearly 1 meter per second type of thing, which would have got a kind of a big jolt on that landing phase. So these are some of the pictures which has captured when it reached the lunar surface during hovering phase. And here also you can see that how it has given that that offset correction in terms of what we have just mentioned here. And this one sensor became very important because we had a small setback in this particular laser Doppler velocimeter, which is an absolute sensor. This is the first time such a first of its kind sensor which was flown. No other country has flown. Though they have developed some ground-based system, the laser Doppler velocimeter for a space experiment was done for the first time, and this works on the principle of Doppler effect. Basically, light scattered from a moving object experiences a shift in frequency, and this shift in frequency is exploited to evaluate the velocity of the spacecraft or the body. So we got into this subject some 4-5 years back. It was not ready during Chandrayaan-2 time frame, because we need to develop something called erbium doped fiber amplifiers, which were at very primitive stages at that time. So we learned that technology and then perfected such that all this optics was done in a fiber optics domain. And we also developed in parallel, low noise, high gain type of amplifier chains to support this one and to detect very low signals of the order of 1 picowatt. As you see here in this picture, we also had this sensors as 3-channel sensor, a bistatic configuration where transmitters and receivers are separate. That's why it's called bistatic. And then in this sensor on board, it has performed very nicely for channel A and B. As you see here, it is to a perfection. What it was supposed to follow as compared with that inertial sensor of LERAP, it exactly followed that path. For channel A and channel B, we didn't see any deviation. But channel C got into some problem. We didn't get an input because it looks for some consistency checks for 3 times. If it doesn't happen, that input is ignored because we don't have time to look at that. So redundant sensor will come into picture. That is where LHVC has taken over and then given that input, which became very crucial for successful landing. Of course, this is very promising absolute sensors. we have expected this to perform from 2.5 kilometers, whereas it has done from 4.35 kilometers itself as soon as we switched on that, enabled that laser on. And then till touchdown, it has worked. This is one sensor which will work till touchdown, like touchdown sensor. Another important sensor which is done by SAC, Space Application Center, is this LHDAC, called Lander Hazard Detection and Avoidance Camera. This is again a vision sensor, which is based on relative navigation. I explained earlier that during Chandrayaan-2 time, we had an orbiter which had this OHRC and TMC cameras, which has mapped this moon totally. These maps were stored on board in Chandrayaan-3. And as this spacecraft of Chandrayaan-3 approaches lunar surface, the picture of lunar surface is taken and compared with that onboard stored images to ensure that we are in the right location. So this way, we had a strip of about 4 kilometers by 2.4 kilometers on the lunar surface, which we have mapped clearly where are the hazards present and where it is safe to land. And essentially, this camera operates in two modes: 3D mode. That is what I explained now, where craters and boulders will be clearly projected and seen as a 3D object when we do this processing as a DEM. And then in case it fails, it gets into 2D mode of operation, where a flat image will be taken as shown here. So where red zones will be like hazard zones and green zones are safer. So this OHRC ortho map is the one which really helped to assist this camera to get into this. We never got into 2D mode. We were very safe in 3D mode itself, and we could identify our landing very clearly. And these are some of the performance specifications what we have given for this, and everything to a perfection. So let me now come to the real action. What was told as a kind of a trauma or a kind of 18 minutes of terror, what was explained by our beloved chairman, Somnath sir. So this is very important here. See what has happened here during the descent phase. Already we came around 25 kilometers, I told. Because of drift, this has already, once again, the spacecraft at that low lunar orbits will be drifting heavily. So it went back to 30 kilometers. From then on, we started this, power descent phase, wherein this can be partitioned into 4 important phases: the rough braking phase, the attitude hold phase, then we have this fine braking, and the final descent phase. So during this rough braking phase of idea is to kill the both horizontal and vertical velocity to make it near zero. That is a objective of this particular power descent. And in the rough braking phase of about 690 seconds, we have estimated all the velocities, what is determined by this LERAP, and then we got this particular phase done smoothly. And here you observe this from horizontal condition, where normally in orbiting it has to be turned vertical. So 90-degree has to be coordinated very nicely with the kind of velocity inputs from these sensors. If anything happens, then it will become counterproductive, and then it will, what exactly happened in Chandrayaan-2 would have repeated here also. But this is where I think our sensors input, has been to a perfection to see that, as it rotated, velocity sensing was made to a perfection. So during this attitude hold phase, we ensured that all the sequential sensors as planned, like, one is that LASA was switched on, followed by our LDV, and then LASA. Anyway, star sensor, we have much before this, we have taken an input, and followed by that, we also had this, RF based this one altimeter that also has taken an input. And then we entered with all these inputs taken in the NGC loop. We transited smoothly to the fine braking phase, and then we turned totally vertical. Almost the velocities were close to zero. If at all anything, it could be negative velocities only here. And then during this phase of 12 seconds of hovering was allowed during the first 800 meters height. So this was the time where 2 of the engines, so there were 4 engines, liquid engines, 2 of that were shut down, and then only with the 2 we have to come down now. So during the hovering phase, we we went through the inputs of our LHVC as well as the other sensors. We were quite successful. We came down to 150 meters. One more hovering was done for a very short time of 22 seconds again. And then there was one more option of retargeting in the event that LHDAC, that hazard avoidance, finds some hazard there. Then we can do a retargeting, but it was not necessary in the actual lunar touchdown. We didn't experience this retargeting. Instead, a correction from the LHVC was taken for a short time, and then we went down. And then as it touched, the first leg of the spacecraft has touched, and that was sensed by the touchdown sensor. And we have also programmed in such a way that unless two legs touch, we are not going to shut off the other two engines. So as soon as that other leg came into picture, then it was like first leg landed, other three legs almost came simultaneously, and then engines were shut off. So it was quite a smooth landing. And I have just wanted to, this is something in a treat to watch. Kindly see this for about 2 minutes. See how it has landed with two engines and very smoothly touchdown has happened. This is a simulated one because we cannot take a picture directly. Vision cameras will not work with that lunar dust. And this is how that primary ramp deployment has happened. Secondary ramp also joins together and then comes down totally, and then very smoothly it has happened. It was around early morning on 23rd of August. We were all watching with excitement, and then this rover was deployed. A solar panel opens, communication happens with lander, and the rover gets its power, starts deploying down. And then we moved about 4 meters. Now the actuals will come once this deployment is over. You will see the actual picture, not the simulated one. This is we also had some 4 special cameras, lander imagers they are called, so which has captured this ramp deployment. This is as recorded by that lander imager, a true one, how that rover was deployed. That rover power on, rolling down from lander ramp, and it went through a distance of about 4 meters. And then there was a in-plane turn also. Up to that, it is captured. Went through about 4 meters, and you'll see one in-place turn there. There was such an excitement on that day, early morning. People, we didn't know how we lost our sleep also. We were, it was like a nail biting. Even cricket matches, what we have watched, it doesn't give this kind of excitement. And this is one success where, immaterial of caste, creed, or religion, every country, every countryman joined together to celebrate this success. And this is the one which is captured as an STK in our ISRAC located at Pina, Bangalore, where this clearly said we have landed safely. Horizontal, vertical velocities were 0, altitude was 0, and touchdown was successful. And this is how the first lunar land picture was taken. So if I have got some more time, I wanted to capture some of this which was done with rover. Hope I am left with some more time.
Sir, 10 more minutes.
Yeah, exactly. Okay, good. So as the rover went through the lunar surface, it has turned back and it has captured a picture. How it has happened? This is through a system called navigation camera, which was developed at our LEOS. So wherein it's a stereoscopic pair. So it's called the navigation navcam. So it takes a right and left image, and then we also have written down how to create a digital elevation map of this one to create a true ortho rectified map of lunar surface. And that is the one which has captured this lander rover. After going through the distance, it has captured this lander picture. And this is some of the path planning also has to be done for the rover to move safely. It should not hit a rock or it should not fall in a crater. So we have to carefully plan with this navigation camera only. So that this camera aided to go through about nearly 120 meters, more than what Chinese have done. So they have done up to 80 meters. We moved our system more than that. So some of the scientific instruments which we have used in this rover are this Ramba, which is a Langmuir probe to do surface plasma studies on lunar surface with respect to time. We also had this Chaste payload for thermal property studies, and the ones which are marked in different colors, the ILSA, instrument for lunar seismic activity, is done an instrument developed by LEOS based on MEMS technology, which I'll explain a bit later. It is for studying of seismology of moon. And also we carried one more, a passive payload called laser retroreflector array supplied by NASA, which is put in moon today. And then we also had this alpha particle express spectrometer, which is a rover payload, and LIBS, laser induced breakdown spectroscope, is a special instrument. For the first time, such an instrument is flown in a rover, and this has also, done some elemental identification and abundance. And also we had one more special payload called spectropolarimetry of orbitable planet Earth. That means this scientific instrument was in that propulsion module. From there, from lunar surface, it will study about Earth surface, whether any kind of signatures are present both in terms of Earth surface or any other habitable planets around our particular universe to a certain extent. And I'll just take a few minutes to explain this very important sensor, which is meant for lunar seismic studies. It is called ILSA. So mainly its main objective is to study moonquakes. So this is a MEMS-based technology wherein we use technologies of silicon bulk micro machining, and also we need to do some kind of a bonding, anodic bonding, silicon on glass. It follows the whole lot of photolithography process, and 6 such it's basically an accelerometer, because as you see here, it's a comb structure which has got some fixed electrodes with respect to movable electrodes. So any deflection will be a measure of how much it experiences under gravity. So essentially, any kind of disturbance will lead to this kind of a cantilever depression, and then this works on the principle of capacitive sensing, a capacitive transduction. So this has a capability to resolve even 100 nanoG, what we have seen per root hertz. This is the resolution what we could test. One of the best labs in CPRI at Bangalore, this was tested. Better than that we could not do, but on a lunar surface we have seen that we could go up to less than 10 nanoG also. So this has become a very good calibration. Lunar calibration was done for this instrument, and this works on a direct contact with the lunar surface. It consumes very less. Being a MEMS device, it is a very small device. It has less mass and then very low power it has for. As you see here, how small it is with respect to scale. We had one fine sensing as well as one coarse sensing thing, which has been organized in a hybrid microcircuit system to see that a system does to a perfection. So this is one sensor which can even be switched on during our maneuver time. So one such thing is captured here when that rover navigation happened. What you see as a spike is an event there. If you have triggered anything to turn or anything, that is will be captured. And what you see as a broad thing is the basic noise of this one. We also had one opportunity to create, to record one unidentified event. We are still on studies to confirm whether it is a natural event on lunar surface or it is something related to thermal phenomena. So this is a very useful instrument which has done some lunar seismic studies. Followed by this, we also had one important instrument called laser-induced breakdown spectroscope, again done at LEOS. So this is another first of its kind, in situ elemental identifications spectroscope. And what it does is a high power laser, hits the lunar surface, creates a plasma. And during the ionic emission, this plasma within this transient dying time, this will the spectrum will be captured by another optics, which is a collector optics, and then this will be fed to a spectroscopic system inside this particular instrument, which essentially is a grating. We have used a holographic grating in this case, and then a lot of lenses and mirrors were used for this one. And this is how we could capture the first instant of what kind of elements are present. You could see that several compounds of iron, sulfur was there in abundance. Chromium, calcium also was seen. Of course, several other data is still under investigation with both ISRO as well as other academic institutes to find out what compositions are still present on the moon. Our interest is mainly towards finding hydrogen and oxygen. Of course, many oxides were seen, but not as hydroxyl molecules yet. But still investigations are on. We have to confirm that. And just before completion of its life, we also did one experiment with that lander. What we did is called a hop test. That means when it completes that 14 lunar days, that means the entire 14 days will be sunlit condition there, and the next 14 days will be dark condition. So just before shutting off our systems, we did one exercise called hop test. So what we have done is we lifted that lander to a certain height of about 0.3 meters and laterally translated by around nearly about 0.2 meters and then once again landed. So this is evidence of how we have done that pre-hop image to post-hop image. You can see that that particular lander leg, how it has been displaced with the trail marks of that rover getting displaced. So this is a very useful experiment because for future lunar missions, if you have to collect something like a sample and then come back to Earth, this exercise will be a prelude to that, and we'll be very sure that how like the way a descent module has happened, how an ascent module can take off without any difficulty. So we got confidence now that in our future lunar missions, certainly in terms of whether it is going to be a sample return type of mission or it is going to be a human landing, we are very sure the kind of sensors what we have used and several other subsystems, the navigation control systems, and the kind of softwares we have written, we are very confident that future lunar missions of India is going to be a great success. With that, I'll stop my presentation. Hope it has given enough information for this India's lunar missions. I have captured everything in this particular set of slides. And very importantly, I have captured this electro-optical sensors, which played a key role in the success of this particular mission. And thanks for all your attention. Thank you so much. You can now ask me, if you have got some queries. Thank you all. Thank you so much.
Thank you, sir, for the very interesting and informative session on Chandrayaan-3. Now the session is open for discussion. The audience can ask the questions.
Hello. Yeah, Professor Sivakumar. It was very nice talk and very informative. And I think it was whatever we are looking for, a wonderful talk for a long time. And you could explain it, you could give a clear view of how starting from the Chandrayaan-1 and then Chandrayaan-2 and what was the reason for the failure of these two and what happened based on ways, how it was taken care in Chandrayaan-3 and it successfully landed did the landing. But being actually it was more like a technical thought. So being a physicist, actually we would wonder that how the successful landing was different, making different India. What was the actually reason? What information we got based on which the India is different from other countries? I think I could understand towards the last of your presentation. You mentioned that there are we can also trace some not only taking other than the taking the pictures. So we could understand what are the constituents like different materials, different elements and so on. And you are looking for whether the presence of hydrogen and oxide is still there. And then we were also explaining about the hop test, and which is most important. But what information we can get, and based on which why the Chandrayaan-3 is landing of the Chandrayaan-3 is unique and different from other countries. That way, India is, I mean that India has come in the number one list in the world. How we can say that it is different? What information we got, which is basically unique?
Yeah, I got your point. See, when it comes to these kind of very special missions, country's pride is first priority. If you want to buy such kind of sensors, if you have to really venture into lunar missions, it's not straightforward for you. Okay, countries will first of all say that we ourselves have to perfect. We have done 1 or 2 missions. We can't spare this kind of sensors, so we are forced to develop such sensors to assist this landing first of all. So this is something which I explained. Each of the sensors, they were all unique and developed at different units and centers. And we ourselves, though initially during our Chandrayaan 1 phase, we took some help from NASA. Certainly, how to maneuver and then go through a interplanetary type of transit, this one maneuver. Certainly, we have to get help from other countries. But then when it comes to maturity from Chandrayaan 1 to Chandrayaan 2, we ourselves made some of these sensors. But then again, we got some assistance from NASA how to that navigation systems, especially that filters which are used in navigation. We were also slightly worried about whether everything should happen in sequence without any kind of thing. For that also, I think we resorted to NASA's help. Whereas Chandrayaan-3 was purely indigenous effort. Absolutely no support from anybody except for some ground stations which have to receive the data. As the maneuver happens at different Earth orbits, we need to have different receiving stations. That mutual kind of cooperation always exists. So one thing is going through this particular a scientific mission where we need to cross over from one planet to another planet kind of thing, though not a planet here, but certainly it calls for a different dimension in terms of development of all subsystems, including sensors, which is unique to ISRO now, because now NASA themselves has come forward that some of the sensors which you have used, we are very interested to know about its technology, and then we wanted to buy from you. This is what it has been told. So a lot of interactions have happened after our beloved chairman as well as Honorable Prime Minister visited US. They are very interested to do further collaborations, and Artemis, which is one of the NASA's future mission, which is going to take humans to space and make some studies there. They wanted India to go, participate in that kind of missions. So this is the level of the global cooperation which it initiates this kind of lunar missions. It's not just confined to that. Once we land in a lunar surface, essentially we are forced to make some studies.
Yes.
Our idea is human is always there to explore something different. We wanted to see. We have seen conditions where how whether Mars is habitable or Moon can be something like a transit orbit for which humans have to stay for some time and then go to Mars. This is going to be one-stop shop kind of a thing. Okay. So essentially, these are all the things which comes into, and it should be conducive. As I told, 14 days of sunlight and 14 days of darkness is something where we have to make some lot of studies in future. So it create a lot of interest towards all communities, global communities to come together to make such kind of studies together.
Nice, thank you.
Sir, one question.
Yes, please.
Sir, Chandrayaan-3 is the exploration is taking place in the South Pole, right? In the South Pole of Moon.
Correct.
Yeah. Could Chandrayaan-3 find any new element there in the South Pole? And also, what is the significance of the South Pole, not North Pole?
Okay. One thing is South Pole, as you view from Earth's thing, it's the other side of the moon. Okay. So what is told about is anyway other landings have happened in this particular North Pole and all. So there is nothing to find different from that. whether South Pole has got something. And as you have seen in Chandrayaan-1, that impactor created that there is a scope of, water at some point of time. It has been seen on lunar surface. The impactor in its first impact itself, we were lucky to see that. But unfortunate that, such a big thing, whether in Chandrayaan-2 or Chandrayaan-3, though we have landed, hydroxyl ions are not seen in abundance. But certainly we'll look into further explorations where really, this is only a small portion of this particular lunar South Pole, which is about 60 kilometers from the exact South Pole. But certainly I think future missions and with the large roving capacity, we may be in a position to see better than that. But there is, except for chromium and sulfur being in abundance, I don't think any other major element is seen in this.
Okay, sir. Thank you.
So the journey is not yet over. As you said that you are further exploring, like what are the additional information based on the current present data.
Right. Yeah. Still, it is not over because plenty of data we have got in that 14 days. So it is all given to them. But we have to. Nothing enterprising has come so far. Let us see. Let us wait and see.
So actually, this is Chandrayaan-1 and Chandrayaan-2. Like Chandrayaan-2 was unsuccessful during the last moment, like when the separation happened. So that was taken care and in the technology which was fitted in the Chandrayaan-3. So is there any like whatever the physics principle based on which that how the Chandrayaan-3 is different from Chandrayaan-2, which was not successful, because of which it was not successful? In Chandrayaan-3 it was taken care, and is there anything like we can explain?
In fact, physics, if you look at, okay, it's a technology mix.
Definitely, yeah.
Which comes, eventually it comes from some kind of physics background only.
Yes.
So I was explaining this, this integrated cold and integrated hot test in my slides. So there we got a lot of learnings. For instance, one such thing was microphonics. When we made this laser Doppler velocimeter, we found that this fiber optic system gets influenced by vibrations when we do test on ground. So then we found how come when we do this one on lunar surface, how it's going to be there. Then we found out by segregating the test vibration in terms of the frequencies, what belongs to microphonics. Then we did some ultrasonic specific tests where we found that if you give a isolation to this microphonics, then it is not sensitive, and which is not going to happen in lunar surface. Only on Earth surface this is vulnerable. So, and it has really proven there, yes, there is no microphonic effect. We didn't give that isolation there, and there also it happened. This is one clear physics concept which is learned with this new sensor LDV. And what is different, you told, no, LDV itself was not available for Chandrayaan-2. Actually, this is one sensor which happens to be absolute velocity sensor.
I see. Okay.
Which
there are more questions. There are more audience waiting for the question.
Okay.
So shall we move on to the next question? Dr. Sharad Kumar.
Yeah, first of all, thank you, Dr. SRIRAM, for this nice talk. Actually, learning that most of these, in fact, all of these sensors are developed indigenously, it gives the same goosebumps that I had watching the real touchdown on screen in the live telecast. And also, I thank Team ISRO for all these wonderful goosebump moments that you give us continuously. And I hope this tradition continues. Regarding this South Pole expedition, I have one quick question. Your rover had solar panels that power the rover, right? And that may be one of the reasons why we couldn't get it back after 14 days. Do you have any programs to work with thermoelectric generators like NASA did for, say, Voyager 1 or their Curiosity rover?
Exactly. That is also planned. Actually, we wanted first a soft landing, which we didn't do during that time. But certainly, if you have ventured into systems which can like we had one kind of warm electronics box. What we did is, before shutting off, this was fully charged and then we closed down. But of course, the communication systems were exposed. We didn't have a system to bend it and then protect it from that exposure to that extreme low temperatures. Certainly, this is one scope where we'll start exploring these thermoelectric devices, which will be of
because as you know, this Voyager 1 has been in service for 45 years now, and it's still giving data. So it's a reliable and proven technology. 14 days is nothing for that. And second thing is regarding your LEOS sensor. I saw that your parameter, the operating temperature was something like 20 degrees to some higher 65 degrees or so, if I read it correctly.
Correct.
But then the surface temperature of the moon is maybe much lower, especially at the South Pole. It may be -13 on average, right? So obviously you should expect some failure of those sensors. But once you have these kind of thermoelectric systems, it can always provide the sufficient heat for upkeeping of your sensors. I hope that may be one nice area where ISRO focuses more. So that more reliable and long-time measurements are possible in future. And thank you again for your wonderful talk. And this is just my 5 naya paisa talk. Okay.
Good. Thanks for your suggestions. Yeah, of course, this LEOS was protected as a system. It was not separately going. It was going underneath that rover. So that way, it was slightly protected condition only. But certainly, I think it has a larger scope in terms of using better systems which can withstand that lower temperatures.
Okay, thanks.
Thank you.
Let's move on to the next. Amrita, can you ask the question?
Dr. SRIRAM, sir.
Yeah.
I heard there are many reasons for failure of Chandrayaan-2. One of that I heard is due to extra braking. That is, they used some 5 retro rockets instead of 4, which was 4 was used in Chandrayaan-3, 5 was used in Chandrayaan-2. That was one of the reasons the failure has happened. Is it so? Is it right?
It is not absolutely true. We felt that the central engine could be dispensed with because it didn't find much use during power descent phase. So we thought in the mass reduction process, this can be dispensed with. Of course, all the other thrusters, 8 thrusters were there with these 4 liquid engines. We felt central engine, but what has happened is during that rough braking phase, everything went through fine. When we came down to that attitude hold phase and then subsequent that fine braking phase, when that lander was tilting towards vertical, that it has given some excess thrust. As you say, one of the engines, we had some kind of wall control, programmable wall control, which was missing in Chandrayaan-2. So it has overperformed and then turned. When it has overturned, what has happened is we are supposed to, give exact feedback about what is the tilt and then make it corrected. But instead, what has happened is it sensed like it has tilted only less, and then in the navigation control loop, it gave more thrust and then started rotating, at a faster pace. So we lost control of our communication, and this was found out to be, that NGC, navigation guidance and control system, should exactly, should have that code where clearly it should distinguish between what is overdone and what is not done. So that is where it failed. That's why they call it as a software glitch, even though it is a overthrust performance. So that is what has led, and then it started rotating and then came down crashing.
Okay.
Hope I have answered your question, right?
I think we are running out of time. Let's move on to the next question. Dr. Karanjit Singh.
Thank you, Dr. SRIRAM, for wonderful talk. I have query as ESA is thinking about helium mining on the lunar surface. So what ISRO thinks about presence of helium on the moon?
Okay, there were certain confusions in terms of whether really helium is present or not. Still, some things are going on unless it is going to be revealed by the scientific community. But if such a thing is that, okay, mining is a different proposition. we have to really see. But certainly, presence of such kind of elements will call for such efforts.
Yeah, yeah. So, how much total distance was traveled with Chandrayaan-3 from Earth to Moon after launching to landing? How much total distance was traveled with?
Roughly about somewhere around 86,000 kilometers or something like that. I don't remember that exact number. If you say in terms of orbiting and all, it will be more. In terms of direct distance,
No, I am talking about the distance traveled in all the, you can say, maneuvers in all the orbits. If we talk about the direct distance, that is okay. Okay, that is only 382 kilometers. But I am talking about the total distance. Yeah.
total distance, I have to have an estimate. I don't remember it right.
Okay. Okay.
Ajit, let's make it faster. Ajit, can you ask your question very fastly?
Sir, it was very nice and interesting talk, sir. Okay. Sir, because I'm doing PhD using this LEOS techniques, I have two doubts
I
about
think
this.
others can mute. The person who is asking question, then only we'll get clarity on that. I request others to mute.
Okay, sir. It was very nice and interesting talk, sir. Currently I'm doing PhD in this LEOS techniques only. So I have some doubts, two doubts about this LEOS techniques. And in this LEOS module, what was the emission detection distance from target to the detector?
200 mm.
200 mm. That is close range.
Close range only.
And another doubt is like this emission peak assignments. These assignments are done automatically by the module or done manually at the lab?
No, what we have done is we did a calibration with variety of lunar samples, simulation samples were available. So that exact calibration was done with respect to all these samples, and then with the noise elimination, background noise elimination, and the peak determination.
This all this done in the lab only after taking the
lab
data.
and then calibrated for this condition.
Okay. Thank you, sir.
Okay.
Thank you.
Let's move on to the last question. Rangarajan.
Yeah, my question is, sir, very good presentation. Thanks a lot.
Thank you.
Can the lander and rover be revived now? And what is its current status?
No, it's I think it has done its service. Had we planned like what Dr. Sharath was saying, we could have planned, for future missions, it will be definitely looked into. We need to have some protective systems to take it inside, not exposed to that extreme weather. But if you ask me that whether revival of this particular one, I don't think it is possible, because we have seen around 3 cycles of lunar cycles we have seen now. So I don't think because these systems, when it goes through low temperature, all this that bonds will get that all the solder joints, everything will get broken. So I don't think it is feasible to come back. There are so many systems which will which are bound for this failure. It's reported that it can withstand up to maybe minus 80 degree and all. But I think practically it has seen around minus 140 degrees nearly.
Oh. Thank you, sir. Thank you very much.
Thank you.
I think we have to go on. So thank you all for the active participation. Now I would like to invite Mr. Rajit to propose a vote of thanks.
Good evening, all. We have reached the end of today's webinar section. I deem it a great honor and privilege to propose a vote of thanks for this great event, ROS 2023, organized by the Raman International Optronics Society, LEOS, in association with Department of Optoelectronics, University of Kerala, India, and the LEOS University of Inaugural, Slovenia. On behalf of the LEOS and the entire organizing team of ROS 2023, I extend a very hearty vote of thanks to our Professor K.V. SRIRAM, Director of Laboratory for Electro-Optic Systems LEOS, Indian Space Research Organization, Bangalore, India, for gracing your important work and sharing with us your findings and opinions towards the talk on Unveiling Chandrayaan-3 Triumph, Key Factors for the Mission's Success. I must mention our deep sense of appreciation for you, sir, for giving excellent coverage to the topics such as the brief of Chandrayaan 1 and 2, the special test and modules used in Chandrayaan 3, mission maneuvers, details of sensors used in it, and the different phases of landing, and details of different payloads and instruments used in it. Once again, we thank you, sir, for your outstanding presentation.
Thank you.
A special thanks to the chairpersons, vice chairpersons, secretaries, and advisory committee members for their encouragement, support, and coordination to make this webinar successful. We are thankful to all eminent personalities, professors, faculties, and students across the world who joined the webinar and participated actively. Thank you all for making today's event successful with your contribution. All the participants are requested to submit their feedback form today itself within 2 hours. The link to the feedback form is available in the chat box. Our next webinar will be on 8 November 2023, Wednesday, that is tomorrow at 7 p.m. IST, on the topic Biomedicinal Facets of Fluorescent Plasmonic Silver Copper Core Shell Nanoparticles by Professor Sip Krishna Kaushal, Department of Physics, University of Technology, Malaysia. The deadline for submitting abstract for the presentation session will be on 10th November 2023. Once again, we thank you all for being with us, and we hope to look forward to your involvement in the upcoming webinars to make this series a tremendous success. Have a good day.